Name is Sam. I'm a climate scientist at the University of Minnesota Climate Adaptation Partnership. I'm going to be talking about changing wildfire risk in Minnesota. So, I'm an atmospheric scientist by training. So, this talk will be from a climate science perspective. You would hear a different talk if you heard about this, from a DNR meteorologist or a researcher who studies plant physiology or fire or forest ecology. So, this is from kind of a climate science perspective. My talk will be split into two main parts. In the intro, I'm going to discuss some high-level points about climate in Minnesota and then some of the details of wildfires here. Second, I'll discuss the many ways wildfire may increase and even decrease in the future. If you're interested in any of the resources I've used here or want to read my slide notes, I can put a link to my slides in the chat, or you can use this QR code that's here. All right, so I just put the link in the chat for everybody. So you can follow along if you want, but I'll put a link at the end of the talk as well. So let's get started. Minnesota has warmed and will continue to warm significantly. Shown here is a map of seasonal temperature change since the start of the 20th century. Winters have warmed the fastest. Um, about 4 to 6 degrees warmer than it used to be 130 years ago across the state. Summers have warmed the slowest, and the northern half of the state is warming more quickly than the south. This warming is projected to continue. Models project a further 3 degrees of annual average warming over the next few decades. The end of the century in Minnesota could be 4 to 8 degrees warmer than the present, depending on how much fossil fuels the world uses. So there's kind of a range, especially as you get farther out in time and things get less certain. Winters are projected to continue warming the fastest, but models project that summer warming will rapidly accelerate, a trend that hasn't shown up yet in observations. So let's talk about seasonal precipitation. On the left is historic change in precipitation by season. All the seasons have gotten wetter, particularly spring and summer in southern Minnesota. Southeastern Minnesota in particular has gotten much wetter in recent decades. Probably not all of this change is because of global warming, and projected trends in future precipitation are pretty different from present day trends. The graphic on the right shows possible changes to monthly precipitation in the coming decades. Models project that winters and springs will continue to get wetter, but that summers will on average get significantly drier in the future. And so here's a place where we should step back and think about what it means to look at climatological averages. It's likely that what these projections are telling us is that future dry summers will be exceptionally dry, but there still will be very wet summers in the future. So we're going to see more year-to-year variability and more swings between extremes. And that's kind of one of the big complications of understanding climate change in Minnesota. It's projected to make us both wetter and drier, depending on the season you're looking at and looking kind of between years. The reason for that comes down to a fundamental property of air. So, for every 1 degree Celsius of warming, air can hold about 7% more water vapor. That means that a warmer atmosphere is able to hold more moisture. So, if warmer air comes from a humid place, like the Gulf of Mexico, or really waterlogged soils in the states south of us, that air is going to hold more water vapor. However, if warmer air comes from dry places like the desert Southwest or the Canadian prairie provinces, there's now a larger gap between how much water vapor the air can hold and how much it is holding. So that thirstier air demands more moisture from plants and soil. So that means that in a warming atmosphere, the odds of heavier rainfalls and extreme fire weather or flash drought are all increasing. And it really depends on where our air masses are arriving from and how air masses evolve in a warmer atmosphere. So let's talk a bit about fire in Minnesota to set the stage for the next section. There's two maps here. On the left is pre-European settlement vegetation types. Yellow is prairie, browns are oak savanna and aspen parkland. Green is maple basswood forest, and the purples, blues, and grays are the conifer forests and the bogs of northern Minnesota. So on the right is an estimate of how frequently fires used to happen within these vegetation types. The scale goes from dark red in an average fire interval of less than a decade to pale pink and white with average gap between fires of a century or more. Fire was very infrequent in the humid maple basswood forests and the wet bogs, and fires happened about every 30 to 60 years up in the northern forests. And then in the dark red part of the map, fire used to be very frequent in the prairies and the oak savannas. Um, so little over 100 years ago, in response to a stretch of particularly bad fire years, U.S. fire policy changed significantly. Starting in 1911, burning for land management purposes and indigenous burning was banned. And in the following decades, many more resources were put into aggressive wildfire suppression. Consequently, many forests in the U.S. have a large fire deficit. This fire deficit has meant that forests have become very thick with vegetation and less patchy. When a drought happens, these heavy continuous fuels provide support for rapidly growing wildfires. Out west in places like California, the fire deficit, along with climate change causing an increase in drought and fire weather days and bark beetle infestations, have all combined to create the mega fires that cause so much harm. So the story of fire risk is both about climate change as well as land management decisions and kind of the history of the forests that are there today and how they got to the point where they are. So there's some tools that let us map present-day wildfire risk. This is a map of wildfire hazard potential, which is a number generated by wildfire models that takes into account things like recent vegetation conditions, average weather, and ignition causes. So most of the northern half of the state has some wildfire risk. Northwest and northeast Minnesota are the kind of the hot spots of wildfire potential. The Northwest has multiple ecosystems that are fire prone. Seasonal wetlands that get really dry in early spring, aspen parklands, and prairie. The Northeast, of course, has conifer forest that hasn't burned in a long time. The rainy Southeast has very low risk, and the agricultural parts of the state are deemed zero risk by this particular tool, but depending on the time of year, crops like corn can burn. So that's kind of missing from this risk evaluation tool. So this map is a nice starting point to think about the broader patterns of wildfire risk, but it's definitely flawed. So let's talk about kind of some of the failures of these sorts of risk products, particularly in a Minnesota context. So spatially, these tools are really precise. You can get down to the address level, but that precision is misleading. The modeling that creates these maps is based on forest health data that's mostly derived from satellite measurements. And a lot of that forest health data for the present generation of these products is from 2022 or earlier. And so you're missing kind of 3 and now 4 years of things like drought stress, attack from forest pests, and weather damage, blowdowns, and things like that. So these national products, because they're so big and they're ambitious and they cover so much space, they simply don't update frequently enough or have enough kind of these local details that are important at the scale that we care about. An example of their failure is shown on the right. So this is a map of the final perimeters of the Camp House and Jenkins Creek fires overlaid on the wildfire hazard potential score. The area these fires happened in last year were ranked low and very low risk. So that's kind of the light green and the dark green on this map, and the fire perimeters are in red. So obviously this product did not sufficiently prepare people in St. Louis County kind of for the fire risk that happened last year. And I've heard secondhand that people on the ground knew these forests were very sick with spruce budworm damage and really ready to go up in flames during that dry May last year. So state and local knowledge is definitely more useful than a national product, but sometimes a tool like this is all you have to work with. So it's good to remember what tools like this are missing. This graphic shows the number of historical red flag warnings issued in Minnesota. So months are on the x-axis going left to right, and years go down from the top to the bottom. Red flag warnings are the National Weather Service product that describes days when fires can spread rapidly. So they're specific to each weather office. Different thresholds are key for dangerous fire weather in, North Dakota than it is for Florida, than it is for Iowa or Minnesota. So each office kind of monitors different thresholds for red flag warnings. In Minnesota, peak fire weather happens in the spring after snowmelt, but before green up and the summer rains. So you can see that on this map with a peak in April and May as peak red flag warnings. This year, we actually had a February red flag warning, kind of the first since 2006, which is when this record starts. So it's possible it goes back farther. And we also had six red flag warning for different parts of the state issued last Saturday. So fire season has started here, of course. It seems now like we've switched into a pretty soggy pattern. We're getting multiple rounds of rainfall and snow. So probably the rest of April, maybe even early May, should be pretty quiet from a fire perspective. Continuing along the graph, left to right, there is a secondary red flag peak in autumn after the summer moisture has dried up and autumn winds start to strengthen. The state climate office has noticed a drying trend in recent Octobers, so maybe we'll see an uptick in late summer and autumn fires if that trend continues. A big part of wildfires is not just the weather and vegetation conditions, it's also ignition. So in Minnesota, about 2% of wildfires are caused by lightning, and the remainder are due to people. Burning that gets out of control causes about a third of wildfires. So kind of burning a junk pile or slash. Malicious fires are another quarter, and then things like vehicles, campfires, trains, and discarded cigarettes are also important. Let's look at some recent significant wildfires in Minnesota. So I'm going to narrow down on the last 25, 26 years to focus on modern kinds of wildfire and kind of separate out the enormous fires that used to happen during the clear-cut years, like the Great Hinckley Fire. So the biggest recent wildfires in Minnesota have all happened in the Northeast. And so let's go through this list of fires here that's shown on the map on the right. So going from north to south, the Cavity Lake and Ham Lake fires happened in back-to-back years in 2006 and 2007. They both happened at the site of the 1999 derecho that downed hundreds of thousands of acres of forest across the Boundary Waters and the Ontario wilderness, just this huge storm. All that downed wood needed about 7 or 8 years to cure and get dry and become a huge wildfire threat. And then the Cavity Lake fire was started likely by lightning and Ham Lake by an unattended campfire. The Pagami Creek fire moving south is the largest modern wildfire in Minnesota. Happened in 2011 during a drought and an extreme fire weather event. And it was started by a smoldering lightning strike. Moving south once more, the Greenwood fire 5 years ago happened during an extreme drought and was also likely caused by lightning. And then coming down to last year's fires, the Camp House and Jenkins Creek fires, these happened in an area of extensive spruce budworm damage. And there was mild drought last May, but it wasn't too serious. But there was very extreme fire weather. Camp House was caused by an unattended fire, and Jenkins Creek, I believe, has now been determined to have been caused by a discarded cigarette. There's also significant fires farther south in Minnesota. Here are some of the bigger recent ones that have happened outside of northern Minnesota. Fires that happen on federal land get mapped and included in big databases that make them easier to kind of dig up information on and to put on the nice maps that I showed in the previous slide. It's more difficult to get information on other wildfires in Minnesota that don't happen on federal land. So here's just an example of three that happened out of the Northeast in the last since the turn of the century. On the right is a perimeter of the Green Valley fire that happened near Park Rapids in 2013 when it was pretty dry, and that fire burned 7,000 acres. And then the other two fires are, I show news clippings from them. They both happened in Anoka County in the metro area, and they happened on the perimeter and within Carlos Avery Wildlife Management Area. And so both of these were human caused. One hit 8,500 acres and the other hit almost 2,800 acres. So I'm not going to talk as much about fire risk specifically in central Minnesota forests, but much of the risks I'm discussing today are relevant for most forested places and non-forested places. So there's definitely reason to think that fire risk could increase even in less fire-prone forests. So let's shift to talking about the future and how wildfire risk might evolve here in Minnesota. I will talk about factors that may increase the amount of fuel available to fires, namely more dead, stressed, and damaged trees. And I'm also going to talk about how the amount and intensity of fire weather will likely increase. I'm going to talk about how future forest changes may feedback on wildfire risk, kind of what trees will grow up in the future. And then lastly, I'll talk a bit about Canadian wildfires that happen elsewhere but pollute our air. So, possibly the most significant way climate change is going to impact our forests is how it changes drought. Projections of future drought are complex. This graphic shows change in soil moisture by the end of the century under a high warming scenario. So this is kind of an extreme scenario, but it's sort of the direction that we're headed. We may not get all the way there, but we will get some shade of of um, of this type of change. So on the left is changes in surface soil moisture, about the top 4 inches, and on the right are changes in total soil moisture, so the total soil moisture column. In Minnesota, which is highlighted by a red circle in both of these maps, surface soil moisture is projected to decrease in response to drier summers, but total soil moisture is projected to increase in response to more average annual precipitation. So, depending on how exposed you are to that dry atmosphere, the part of the soil moisture column will respond differently. And so you can see how different types of trees might respond differently to shallow soil moisture being dried up, but deep soil moisture still being plentiful. So um, kind of the first thing that you would think of is that like deep-rooted oaks might do a better job surviving than trees with shallow roots. Thinking about peak fire season, future springs will see more average precipitation most likely, but snowpack will disappear more rapidly. And so we're going to have very high spring drought risk in years when rains are slow to arrive because the snowpack is going to disappear more quickly. In addition, future droughts will arrive more quickly because that drying power of the atmosphere is increasing. It's a phenomenon called flash drought, so drought that can appear in the space of 2 weeks. Again, stepping back from projected changes in averages, it looks like what the science is telling us is that we'll have more rapid and extreme swings between wet and dry. So severe and extreme drought conditions will take much less time to establish in the future with a warmer atmosphere. It's not just drought risk that's changing. We are unsurprisingly going to see more extreme heat in the future. The graphic on the right is from the State Climate Office, and it describes our historic July 1936 heat wave. It shows daily high and low temperatures in downtown Minneapolis. There are almost 9 straight days with highs above 100 and 7 straight nights with lows 80 degrees or higher. Few people alive today have memories of how bad Minnesota heat can get. Most of our heat records, our all-time temperature records, were set in the 1930s. Climate models say we'll start to break these all-time high temperature records over the next 20 years, and we're also going to tilt the odds towards extreme heat waves like this one. So this really unbelievable heat is going to start returning in the future if we kind of continue on the pathway that we're on. Heat waves and drought are tightly linked. Low soil moisture allows hotter afternoon temperatures, which in turn further dries out the soil. Two or more extreme events happening at the same time is called a compound event. So an example of a compound event is a hot drought. So that's when a heat wave happens at the same time as a serious drought. Compound events are particularly harmful to living things. For example, during a hot drought, trees lose water at the same time water is in short supply, which potentially damages the tree and it leaves it with less resources to respond to pests and disease. So if you're kind of responding to multiple things, then if a third thing comes along, your defenses are down. So forests across Minnesota are still recovering from the hot and dry summer of 2021. So I think a lot of us are still seeing the effects of our most recent hot drought. Another climate-linked threat to trees is pests. The first pest I'll talk about is spruce budworm. So that's a moth that feeds on new needles in the larval stage. They preferentially feed on balsam fir and to a lesser extent white spruce. We're at the southern end of their range, so it's actually unclear if climate change is necessarily going to help them in the long run. Spring and winter warming are particularly important for the timing of tree pest emergence. So, on one hand, warming may make budworm emerge too soon in the future, when they would still be vulnerable to the last hard freeze of the season. On the other hand, warming might speed up black spruce emergence in the future so that it syncs up better with budworm larvae emergence. So, the way that warming differentially impacts the different species involved may change the response of budworm and its host plants. The graphic on the right is from the DNR's Forest Health Survey and shows the number of mapped acres impacted by spruce budworm. You can see that spruce budworm erupted in recent years, likely aided by the extreme drought in 2021. Um, I think with spruce budworm, lots of factors are at play. Even if it gets kind of warmer than spruce budworm would like, there's still plenty of drought-stressed trees for them to feed on, so they'll still have a big impact, even as their preferred range shifts north into Canada. So another important tree pest is emerald ash borer. The graphic on the right shows where emerald ash borer was seen before 2025. The counties in gray, and then the yellow counties are where it was first found in 2025. So you can see it's expanding. The climate story for emerald ash borer is pretty simple. The invasive beetle doesn't like cold winters. So as winters get warmer, more larvae survive. There's a higher population that can attack more trees. I believe for people who work in forests, the really concerning thing is when the emerald ash borer gets a foothold in the black ash forests of northern Minnesota. And so a lot of people are developing plans for when that comes, and those forests get hit really hard by the borer. The last pest I'll talk about are tamarack pests. So since the year 2000, over 1 million acres of Minnesota tamarack forest have been impacted by the eastern larch beetle. The beetle had previously been considered benign, only boring into the bark of damaged trees, but now over 90% of Minnesota's tamarack forest has been impacted by them. And again, their climate story is pretty simple. A longer growing season means they now have enough time to give birth to an extra generation, as shown by the graphic on the right. So this is a phenomenon called bivoltinism, so they can um, increase their population just because the growing season is longer. Another tamarack pest is the larch case bearer. Um, it's a non-native pest that's aided by warmer winters and drier summers. The number of acres impacted by the case bear have more than doubled since 2020. It seems likely that this is partly a response to the severe drought of 2021 again. So I'm definitely leaving out a few important tree pests in this discussion, things like forest tent caterpillars and the spongy moth. As far as I know, the direct climate impact on these species is less well understood, but their damage is definitely amplified when trees are drought stressed. So the background of all of these issues with tree pests and tree disease is that as drought stress increases, the trees are more vulnerable to all these pests. I'll just talk about one tree disease today, oak wilt. So oak wilt is a fungal disease spread through roots or by beetles that spread it between bark wounds. It infects all oak species, but it's particularly harmful for red oak species. On the right is a map of oak wilt spread in Minnesota. Areas in black are where it's well established, and counties in gray are where it's been found. The beetles that spread oak wilt are helped by warmer winters. I think they're both non-native, the main vectors, and so they're just better able to survive our new warmer winters. And additionally, there will likely be more bark wounds to spread between trees, and those bark wounds will probably be caused by an increase in weather damage. So that brings us to how climate change might increase weather damage to trees. So weather damage can kill trees outright, or it can cause damage that exposes them to other threats. So first, I'll talk about how thunderstorms might change in the future. The science of future thunderstorms has rapidly advanced in recent years. Thunderstorms require heat, humidity, and certain types of wind to form. So on the times of year when we get air from the Gulf of Mexico, that air has more warmth and it has more humidity, which means more fuel for intense thunderstorms. So we're projected to see more frequent and more intense severe thunderstorms in the future. Our main thunderstorm season is May through September. And with climate change, that's going to expand, and we're going to see more spring, autumn, and even winter severe thunderstorms. On March 6th of this year, Michigan had its earliest EF3 tornado on record, and a few days later, on March 10th, Illinois set the state record for largest hailstone with a hailstone that was 6 inches in diameter and weighed a pound. I think it beat the previous record by about an inch and a half. So a very impressive record. Those types of events, really severe weather earlier in the year than it happened in the past, I think they're a sign of the direction that the upper Midwest and Minnesota are trending. So here's a list of changes that we might start to see in the coming decades. Climate change is projected to make large damaging hail more frequent in Minnesota. The picture on the right is from the Wisconsin DNR, and it shows hail strikes on a young aspen tree. So you can see the big gouges that hail can cause. Interestingly, we're expected to see more lightning in the future. So we get more thunderstorms, we get more intense thunderstorms. We will likely see more lightning. And so that would be important for remote wildfire starts. It does seem like people cause most of the fires, of course, but the lightning caused fires can be pretty important in the backcountry. It's still unclear what's going to happen to tornadoes. Tornadoes rely on complex ingredients to form, and not all those ingredients are expected to be enhanced by climate change. It's probably safe to say we'll start to see more tornadoes outside the traditional season, and maybe we'll see a few more tornadoes farther north as you get that kind of warmth that can sustain tornado-producing storms away from where they used to be. And lastly, we're projected to see more frequent and more damaging wind gusts, possibly including more long-lived windstorms like derechos. So that brings me to my next slide. I really want to focus a bit on long-lived windstorms. There's a few different types of storms that produce big areas of straight line wind damage, but the most famous is derechos. That's the one that we hear the most about. Minnesota is prone to big windstorms. The Bemidji windstorm of last June was a derecho that severely damaged almost 12,000 acres of forest. The Bemidji Airport weather station measured a 106 mile per hour gust during the storm. And the weather office up there in Grand Forks estimated that peak wind gusts may have hit 120 miles per hour. My impression is that cleanup from that event, is going to be ongoing for years. But in terms of total damage, that event pales in comparison to the 1999 Boundary Waters blowdown that severely damaged 500,000 acres of the Superior National Forest. And that, of course, doesn't include the damage in Ontario or outside the National Forest in Minnesota. The map on the right shows the damage path in the Northeast and going into Ontario, though the storm did continue all the way out to the East Coast. Red shows severely damaged forest during that windstorm. And as we talked about, this derecho directly led to the Cavity Lake and Ham Lake fires 7 and 8 years later. A more recent example, just south of us, Iowa and nearby states were hit by the August 2020 derecho. This has been estimated to be the most costly thunderstorm event in U.S. history, with over $11 billion in estimated damages. And in a meteorological context, sort of to compare it to those other two storms I just talked about, they estimate that 1.3 million acres experience wind gusts stronger than 100 miles per hour. So it was an even more impressive event than the 1999 Boundary Waters storm. So the reason I did a single slide for this for windstorms and derechos is that very new research has started to find evidence that climate change may eventually make long-lived windstorms like derechos, one, happen more often, two, have stronger winds, three, be longer lived, and because of all that, have a bigger damage path. Um, the evidence is pretty compelling that this is the direction that we're trending, but it's not cut and dried yet. But the reason I discuss it here is because if these predictions do come true, they might be one of the most significant climate impacts for Minnesota forests and Minnesota in general. So one more slide about damage to trees from weather. I want to talk a bit about future winter precipitation. Projections say that Minnesota will get less snowfall in the future and more wintertime rain. Snowfall actually hasn't trended down yet. In fact, the state climate office says it's gone up a little bit in recent years. But over the next few decades, we'll likely start to see noticeably less snowfall on average. As some of our winter snow gets converted to winter rain, we'll also see different snow characteristics. Future snow events may be wetter and heavier. We would see less dry and fluffy snow. Kenny Blumenfeld at the State Climate Office has talked a few times about this event in December 2022, which damaged hundreds of thousands of acres of trees in Minnesota. You can see this picture on the right of damage to red pines in northern Pine County. Lots of broken branches and downed trees, and the damage path was on the scale of a large summertime windstorm. A little bit of extra warmth and wintertime humidity might not just make for kind of heavier snow that's harder to shovel, but also more snow on some occasions. Several studies had found that very large snow events may become more frequent in the future, even as average snowfall decreases. This happens because winter air is dry, so when we do get warm and humid Gulf of Mexico air in winter, it can help tip the scales towards monster snowstorms, if the conditions are right and you don't just move all the snow to rain instead. This effect would likely be amplified on the North Shore, where they already get lake effect snow, and it would be further amplified by the fact that Lake Superior is losing ice cover. So on average, total snowfall is going to decrease in the future, but real big snow events might get supercharged a bit by climate change. So a difference again in the change in the average and the change in the extremes. Lastly, another snow-related concern is loss of snowpack, which protects the ground during cold snaps. As snowpack becomes shorter-lived, fine roots and young trees can take a lot of damage from cold events. Snowpack has already become less reliable across the state because of an increase in winter thaw days, not because of a change in snowfall yet. So let's switch to talking about fire weather. So we talked about how climate change might increase the number of dead, damaged, and stressed trees, which would impact the amount of fuel that's available for forest fires. Now let's talk about how the meteorological conditions that are conducive to rapid fire spread or large fires might change in the future. So meteorologists track a variety of numbers that describe the dryness of vegetation as well as potential fire behavior. One example of a system used to characterize fire risk is the Canadian Forest Fire Danger System, which is shown on the right, one part of their system. The US has a similar system called the National Fire Danger Rating System, but I believe that fire forecasters look at both systems here in Minnesota since our northern forests are similar to Canada's forests, so their models work well for the forest in the northeast part of the state. The Canadian system is also used more in climate research, so that's the one I'm more familiar with and I'll talk about today. But the US system is mostly just different in the details. So the Canadian system starts at the top with weather observations, things like temperature, relative humidity, wind, and rain, and then along with pre-existing conditions. And so you use those things, the meteorological observations, to build what's called fuel moisture codes. So you can see the moisture codes across the middle, the fine fuel moisture code, Duff moisture code, and the drought code. So these describe the dryness of different classes of vegetation. So fine fuels are the things that dry out rapidly and would catch fire quickly, like small twigs, conifer needles, or grass. The Duff moisture code describes things that take longer to dry out, the layer below the litter, as well as bigger twigs and branches. And lastly, the drought code describes things that take a long time to dry out, like deep soils and trees themselves. So you can think of a forest drying out as the drought stretches on. The fine fuels dry out first, then the duff and the smaller branches, and lastly, the branches and the standing trees. So moving down next on this flow chart, the next line combines fuel moisture codes and wind to calculate the initial spread index and the buildup index. So these are two fire behavior indices. The initial spread index measures how fast a small fire would grow, and the buildup index is a measure of how much fuel is available to burn. So kind of how big a fire could get and how extreme of fire behavior would happen if a fire could get established. So these describe fire behavior at different stages, kind of maturity of the wildfire cycle. So these two indices are then further combined into a single measure of wildfire risk called the Fire Weather Index or FWI. And so I put a link to Minnesota's FWI down there. You can kind of click it any day and check what it is right now. I think it's pretty close to zero right now because everything's pretty cold and wet and cloudy. So sort of the opposite of fire weather. So I want to look at a couple specific examples to help us understand what a bad fire day looks like. So last Saturday, March 28th, Minnesota experienced widespread red flag conditions. A weather system with strong sustained winds, strong wind gusts, and low relative humidity passed through. The snowpack had largely disappeared except in northeastern Minnesota, and greenup hadn't started yet. So some of the state is currently in moderate drought, and some parts of Aitkin, Carlton, and Pine currently in severe drought. So we can see what that kind of setup looks like in the Canadian Forest Fire Danger Rating System. This is a printout of the weather stations that experienced the worst fire weather conditions last Saturday, using the Great Lakes Fires and Fuels page, which I've put a link to. Going left to right, we have station name, the date of the observations, the weather observations, and the colorful blocks denote the fire weather risk elements. So these numbers aren't meaningful except to the experts. So for the rest of us, they kindly color code them by danger level. Red and orange are more dangerous, blue and green are less dangerous. Fine fuels were pretty dry, as shown on the left of the fire indices. So yellows, orange, and red. But the bigger fuels, as shown by the Duff moisture code, moving from left to right, the DMC and the DC, still had plenty of moisture. So the most dangerous element last Saturday, the reason why there was red flag warnings was the initial spread index was very high. So pretty low humidity and very strong winds uh, would have pushed a fire fast if it started. The buildup index wasn't very scary because the bigger fuels hadn't dried out yet. So that'd be different if it had happened in a month or something. But all these elements combined into a few places with dangerously high fire weather index is shown in the rightmost of the block columns there. So as far as I know, no big fires got out of control during that event. And I think there was maybe a few 30 or 50 acre fires up north. Um, so let's compare last week's fire weather event to a much more serious stretch of fire weather days, which is May 12th of last year. So this is when the Camp House and Jenkins Creek fires grew their fastest in May of 2025. So we're looking at the same readout from the Great Lakes Fires and Fuels website, but we're now focusing on Northeast Minnesota weather stations. So that day, temperatures were in the mid to upper 80s, and relative humidity, even in Northeast Minnesota, was in the teens. So very, very dry, very, very warm. And there was plenty of wind, with wind gusts around 20 to 30 miles per hour across the area. There was some drought in northern Minnesota, but it actually wasn't that bad at the time. So you can see how this is reflected in the fire weather risk components. Fine fuels were explosive, extremely dry across the entire region. Bigger fuels, as described by the Duff moisture code, were in danger territory, but again, the drought code wasn't too bad. Because fine fuels were so dry, the initial start index was extremely high across most of the region. And unlike last week, the buildup index was pretty elevated because of dry, smaller fuels. And these were all summarized by the very high fire weather index values across the entire region. Um, and you can imagine that for a fire risk forecast, these indices are only the beginning. This is just the kind of weather description of fire risk. Things like forest health and terrain and other local conditions will all change the risk and are the kind of things that meteorologists and forecasters take into account. And then, of course, there's the last component, which is human behavior and kind of random chance. Um, those things are really important in fires, and both of the fires that grew fast on the day that I'm showing here were started by people. Something that's impossible to predict. So we looked at two examples of fire weather, and we looked at kind of the meteorological underpinning of the definitions of fire weather, thinking about fine fuels and bigger fuels and wind and low humidity. And because fire weather has this very technical definition, scientists can look into the future and make a projection of future fire weather conditions. So these days of extreme fire weather are projected to increase. This increase is driven by several things, hotter, more days of very low relative humidity, a possible decrease in average late summer and early fall precipitation, and faster drying of both large and fine fuels, powered by this atmosphere that can be thirstier when it's really dry. So the graphic on the right is one analysis of future fire weather from the National Climate Assessment. The left map shows historic number of days of extreme fire weather, and the right map shows relative increase in number of days of extreme fire weather by mid-century under a high warming scenario. You can see that Minnesota is projected to see some of the largest relative increases in fire weather, along with northern Wisconsin and parts of Michigan. A 500 to 1,000% increase in days with extreme fire weather. Kind of, so that's what this graph is showing for Minnesota forests. Another important thing, kind of not captured by this graph, is that the fire season is going to get longer in the future. So in warm and dry years, fire weather could pop up in more and more of the calendar than it did in the past. And unlike some climate change things that are harder to detect, this change is likely happening now or very soon in Minnesota. Um, Other fire-prone parts of the world have already seen observably worse fire weather due to climate change. Places like California, Canada, Australia, Brazil, and the Mediterranean, their fire weather has already kind of observably gotten worse because of climate change. So part of the future increase in fire weather is because the atmosphere is expected to be drier on the driest days. The other part is that it will be very easy for fuels to dry out in the future. So shown here is 100-hour fuel dryness, which is an estimate of the amount of moisture in vegetation that is 1 to 3 inches in diameter. So this is analogous to the moisture codes we discussed in the last few slides. Along with 100-hour fuel dryness, there's often 10-hour fuel dryness and 1,000-hour fuel dryness. So those describe the amount of moisture in different diameters of vegetation because bigger vegetation takes more time to dry out. So the number of hours the vegetation takes to respond to dry conditions. So the plot on the right shows projected change in average September 100-hour fuel moisture for St. Louis County um, in the historical period, now and into the near future, and then about 30 years into the future. Moisture is on the y-axis, so the lower you go, the drier fuels get. Most models project that average summer, autumn, and spring fuels will get drier in the future, but again, it's important to think about future extremes. Some future years will be very wet with no fire threat, but future dry years will be very dry with very significant fire threats, more significant than they were in the past. In recent years, wildland firefighters and fire scientists have noticed that fire behavior in places like California and Canada is not only getting more extreme during the day, but also during the night. Overnight temperatures here in Minnesota and elsewhere are warming more quickly than daytime temperatures. And a big implication of that is that overnight fires that were previously slowed down by overnight cooling and humidity recovery can now sometimes burn rapidly through the night. I've seen this called the night breaks of wildfires. So, wildfire behavior calms down overnight, but then can blow up again the next day. But now with 24/7 extreme fire behavior, firefighters don't have a chance to rest. They don't have a chance to get ahead of spreading fires, and it's more difficult to organize evacuations. So you all will know about that, about the difficulty of getting out severe storm warnings for nighttime tornado warnings or severe other severe weather that happens while people are sleeping. Shown on the right is April through October average daily minimum temperatures from 1895 through last year in St. Louis County. You can see that overnight temperatures are steadily moving upwards during fire season here in Minnesota. This increase in overnight burning risk has been well documented in Canada and in the Western US, and it's certainly become an increasing risk here in Minnesota. So let's spend a slide talking about what future forests might look like. Forests are dynamic and ever-changing. And so I think the question is, after decades of milder winters, changing precipitation patterns, pest outbreaks, wildfire, drought, windstorms, along with different management decisions, what are our forests going to look like? The table on the right is from the Climate Change Field Guide for Northern Minnesota forests. It shows 4 projections of climate suitability for different tree species in the northern woods. Red is bad, green is good, yellow is little change. Looking at species that are expected to suffer, quaking aspen, balsam fir, black spruce, and white cedar. These are all species that are not drought tolerant or are slower growing. Trees that might benefit, red maple, oaks, maybe pines. This table mostly captures changes due to changes in precipitation and temperature. It doesn't necessarily include all the elements I've discussed today, like pests and disease and windstorms. So a few things are probably going to happen simultaneously as we move into the future. One, fire-prone coniferous forests will take more damage from climate fuel disturbances, like I've talked about here. And at the same time, in the northern forest, there'll be more competition from southerly species that can survive there in the new milder winters. So those new southerly species that are creeping into northern Minnesota, particularly maples, they make forest conditions that are more humid and less fire prone. So that means that the forests that replace the present-day coniferous forests may very likely be less prone to fast-spreading wildfires, especially if the oaks and the maples win out. That means we might be at the beginning of, something like a 30 to 50-year window of maximum forest fire risk here in Minnesota. So due to changes in forest composition, it's possible that large forest fires would be less likely by the end of the century, just because of the type of trees that went out. But time will tell. Maybe increases in fire weather and rapid drought are more important than changes in forest composition. This dynamic is pretty different from fire-prone grass or shrub landscapes. For example, in Southern California, the shrubs that grow back are extremely fire-prone. Mediterranean climates are caught in a real climate trap. In rainy times, the shrubby chaparral grows back really fast and thick, and then in dry times, that extra growth turns into a huge wildfire threat. And I think for us here in Minnesota, I would guess that grassland and shrubland fire risk will only increase this century. Those ecosystems respond much more quickly to drought and are already fire prone. So definitely northwest Minnesota and other areas with lots of grass and scrubby vegetation. So just the last couple of science slides here. Let's expand our scope from Minnesota wildfires to all North American wildfires. We all know that Canadian wildfire smoke has gotten much worse in recent years. Canadian forests are even more vulnerable to climate change than our forests. On the right is a graph of annual wildfire acres burned in Canada since 1983. You can see that 2023 was a record-breaking fire year in Canada, and 2025 was the second worst. Scientists project that a fire season as bad as 2023 in Canada will become normal in the future. So happening something like two or more times a decade within the next 30 years, and four or more times a decade by the end of this century, kind of on the pathway that we're currently on. So what used to be extraordinary becomes normal in the Canadian forest. Of course, changes in Canadian wildfires have big implications for us here in Minnesota. On the right is a graphic from the state climate office showing the number of days per summer where a Minnesota station registered an unhealthy daily air quality reading. Last year was really bad with what felt like weeks of bad air quality. It was bad in the cities. I know it was even worse in northern Minnesota. Some of these air quality days on this chart are caused by Minnesota fires, but most are from Canadian fires because we import Canadian smoke all the way from Alberta out to the eastern Quebec forests. So there's just this huge area that we can draw Canadian smoke from. It's almost certain that this trend is going to continue. Week-long or longer smoke episodes will probably be a regular occurrence now in Minnesota summers. So that brings me to the end. To summarize, there's lots of reasons to think forest fire risk in Minnesota will increase for at least the next several decades. So I talked about two big reasons. The first was more dead and stressed trees, which means more fuel for fires. And the second was more frequent and more severe fire weather. Vegetation changes to Minnesota forests may alleviate forest fire risk in the distant future, but fire risk in grass and shrublands will likely increase through the rest of the century. And because Canadian forests are even more vulnerable to climate change than our forests, these smoke episodes caused by Canadian wildfires will probably continue for the rest of the century and impact our air quality. So thank you all for coming. I know this is a heavy topic. I help my wife foster cats for a pet rescue here in the cities. These are our most recent fosters, Nectar, Nacho, and Non. They've now been successfully adopted, and their new names are Mackerel, Nimbus, and Marlin, going from left to right. So they've had good names from the beginning, and they'll go into the rest of their life with very good names. My email is pott0150@umn.edu. Feel free to email me with whatever questions you have. I feel like my questions always come up a day or a week later, so feel free to send me an email whenever something comes up. And with that, I'll turn it over to Stacy and look at some of the questions that you all put in the chat.
Well, thank you, Sam. Wow, that was so much great information and some newer information. Yeah, fantastic presentation. We do have a few minutes for questions, and there's at least one in the chat. While Sam is thinking about that, I just want to remind you if you joined later, if you are representing a city or county currently in hazard mitigation planning, you can use this hour as a match time for your grant with HSEM. And also a reminder that we will be posting uh, the the video of this presentation on that the same page where you registered. So I'll put that in the chat again. And Sam, do you see that question there from Sadie?
Yeah, so Sadie asked about surface and groundwater withdrawals or diversions and how that might play back onto wildfire risk. Um, that's a really good question. I think for a lot of these things, they're kind of more at a larger landscape scale. Um, if you get a red flag warning, it's like something that happens over, a 5 to 10 county area or something like that. So kind of the local scale. Um, might not have as big of an impact on kind of larger wildfire risk, but I think anything that affects, forest health and vegetation health definitely would have an impact on like um, local fire risks. And I think moving forward, that's something that's going to be really important to think about because I think a lot of the intuition that we have about the fire risks are for these places with enormous, like millions of acres of national forests out west or millions of acres of forests in Canada. That's like the people that are doing the research and driving the research. That's the place that they're kind of pulling from. Whereas here, our forest is much more fragmented. And so I think the questions are going to be a little bit more different. And so I think exactly what you're thinking of is kind of one of the key things going forward. I could not answer that question completely for sure. I don't know enough, but I think thinking about how fire risk on when, people, woodlot owners, or a state park, or a county park, when it's 250 or 500 or 1,000 acres block that's surrounded by county roads, what is the fire risk with that? That's a pretty different question than like, what's the fire risk, out west in Yosemite or something like that, where the forests extend, north to south across the entire state of California. And so I think that will be a big question going forward and a big reason why I think Minnesota and the Great Lakes, the fire risk here is unique and it's often skipped over in studies about wildfire risk. That's a really good question. I apologize, I can't answer it completely. So there's a question from Bonnie here. Um, a question about wildfire mitigation considerations. Yeah, so I think a big thing for me, and not something again that I'm an expert on, but I know something that forest managers are really thinking a lot about is questions on changing the way that forest management works and like bringing fire back safely in a way that works with neighbors, in a way that works with um, all the impacted parties. So prescribed burning, I know, is really picking up across the state. More and more people are trying to make it work, even though it's not an easy thing to make happen all the time. And a big reason why it's not easy is because a lot of places haven't burned, so you often have to do thinning, either mechanical thinning or hand thinning before you can do prescribed burning. And so a big thing I think going forward is just really thinking about different forest management decisions, because those have really direct implications on wildfire risk. You can see places out west where they've been doing fuel reduction, thinning and burning, which they're doing up north in Minnesota as well. They can stop wildfires dead in their tracks just because that fuel goes away. But those are huge questions. It takes a lot of money. You have to get money, from really big sources to do stuff like that. Those are really ambitious, big things. For smaller things, there's lots of community programs thinking about wildfire risk, and lots of things that you can do on the individual property level or on the community level of building, fire breaks and things like that are really, really useful and help everyone. The DNR has a great list on things that property owners can do. The Firewise program, I think it's called, but there's other programs as well doing community level risk reduction up north specifically. There's lots of resources to start with. This is this is a pretty depressing topic, but I think unlike some climate change topics, there is like a lot we can do to reduce the risk for people, which is really cool. I think there's a lot of things that we can start changing today to make these risks much less impactful over the next 10, 20, and 30 years. So I don't know all the things that we can change, but I would say that one of the positive things is that there are a lot of responses that we can make to this. So I'm glad that you're thinking about that. Thank you.
There was another question about who else do you think should be learning and thinking about this outside of emergency management offices? And you've already answered some of that with definitely like forestry, forest management. But are there other audiences that you wish would hear this message?
Yeah, I think for kind of the general kind of population, definitely people who just own property up north. There's so many things you can do at a property level to reduce risk. They're very well documented. Um, yeah, like I said, the DNR has some, lots of states out west have really nice guides about it. So you can make a kind of a plan around wildfire, both to prevent the risk today, but also like if one happens, what you'll do. I think another thing that I really wish people would know, um, and I know I wish people would understand how seriously public health people are taking kind of the air quality part of it too. Um, it's this direct threat of the flames, but it's also this kind of more vague threat, this spread out threat of the smoke. I wish people understood that, and the fact that that might be the new normal, and just how impactful air quality is on people's health. I don't know if we all appreciate that as much as we should just yet. Um, but uh, yeah, that's a really good question. I really wish everyone would think about this because I think even if you don't live directly in an area that's at risk of burning, I think we will all feel the impact of this kind of for the rest of the century, for the rest of our lives. Yeah, that's a very good question as well.
Thank you, Sam, and thank you everybody for attending today. This was just a great informational session and appreciate your time.
Awesome.
Thanks.